Thank you. My name is Sho Yokota from Meteorological Research Institute. This is the final talk today. Today's final talk. This presentation is not mainly about the method of data assimilation, just consideration of data assimilation for forecasting tornadoes using high-resolution ensemble forecast. So most of strong tornadoes are generated in supercell. Supercell is the storm associated with the mesocyclone. Mesocyclone is weaker, larger mesoscale vortices than tornadoes. Diameter of mesocyclone is several kilometers, and diameter of tornadoes are several hundred meters. So tornado is not directly simulated in the operational numerical experiment. So it is very difficult to forecast. The process of supercell tornadogenesis is shown here. For the first, above 2 kilometer height, mid-level mesocyclone is generated. And next, low-level mesocyclone is generated at about 1 kilometer height. And finally, tornado is generated on the surface. So forecasting tornado is very difficult. One of the reasons is because tornadoes are not necessarily generated even if mesocyclones are generated. In other words, what variables should be collected to forecast tornadoes has not been clarified yet. So I tried to clarify that what is important to improve forecasting tornadoes. So in this study, I focused on the supercell tornadoes in 6 May 2012. In this case, 3 tornadoes were generated almost simultaneously at about 12:30 Japan Standard Time. And southernmost one is estimated Fujita scale F3. This scale is one of the strongest tornadoes in Japan. And in this case, this tornado was observed by the polarimetric radar in Meteorological Research Institute, and there was a very dense surface observation network. So in this study, using these dense radar and surface data, we try to forecast the tornado, and we try to clarify what variables are important for tornado genesis with high-resolution ensemble forecast. We use the data assimilation system, nested LTK system. In this system, operational hourly observation is assimilated in outer LTK with 15-kilometer grid interval. And this dense radar and surface observation every 10 minutes are simulated in LTK with 1.875 grid interval. So 1 hour analysis, forecast analysis cycle is repeated. And we made the analysis at 11 JST. And from this state, we perform the ensemble forecast. And this 11 JST analysis is modified by the observation by 12 JST using the ensemble Kalman smoother technique. And this modified analysis is used for the initial state of downscaling experiment with 350-meter grid interval. Okay, the total number of ensemble members are 33, including the experiment from the ensemble mean. So number of members are 33. This is the result of one of the members. Okay, this red region is a high vorticity area. This vorticity is generated very close to the actual path of the Tsukuba City tornado. But this vorticity, this vortex is not tornado, but mesocyclone, because this 350 meter horizontal resolution is not resolved, cannot resolve the tornado itself. So in this experiment, we perform the 33-membered ensemble forecast. So we can draw the probability distribution of high vorticity area like this. The black line is the actual path of the tornadoes, 3 tornadoes. So this figure shows the possibility of one known forecast of mesocyclones. So, and in this region, we calculated the maximum vorticity like this. So you can see that mesocyclone strengths have large spread. So difference of this maximum vorticity is probably caused by the initial state. So I performed the sensitivity, ensemble-based sensitivity analysis of the mesocyclone strength. So this is the definition of sensitivity of mesocyclone strength to variable x. So this sensitivity is sensitivity corresponds to the slope of the regression line of this scattered plot. So this means that large sensitivity, if sensitivity is large, mesocyclone strength is largely increased by small increase of x. So in this situation, x is important to the cyclone strength. So in this study, we choose low-level water vapor and horizontal wind in initial state as variable x. This is a result of sensitivity analysis. This color means the sensitivity to low-level water vapor and allows sensitivity to zonal and meridional wind. At this time, storm was located here, and the direction of the storm is this direction. And from this figure, you can see the large sensitivity to southerly wind is at southeast of the storm, and large sensitivity to water vapor is at southwest of the storm. That means the stronger southerly wind here and more water vapor here makes low-level mesocyclone stronger. Wind here and water vapor here should be observed to improve forecasting the mesocyclone. But this is the sensitivity of mesocyclone. So we need to clarify the sensitivity of tornadogenesis itself. So next, I performed the higher resolution ensemble forecast here. So this grid interval is 50 meter. So in this experiment, also the number of ensemble members are also 33. So in this experiment, a tornado is resolved. This is a result of one member when maximum vorticity becomes strongest. So that this vortex is located on the line of large gradient of surface temperature. And you can see the near surface vortex is smaller and stronger than upper level vortex. So this is a tornado, and this is a low-level mesocyclone. So to examine the origin of this tornado circulation, we perform the circulation analysis like this. The circulation is the curvilinear integrate along the link, backtracked from this timing. This circulation is only generated by this baroclinic term and friction term. We calculate this circulation in this link, along this link, backtrack of this timing when maximum vorticity exceeds the 0.6 per second at 30 meter height. This is a result of circulation analysis. This black line is the circulation, time series of circulation. And blue line is baroclinic term. And green line is friction term. And the red line is the integrated this baroclinic and friction terms. So this tendency of this red line is similar to the black line. So you can see that from this figure, friction increases circulation, and the baroclinic term is small. This is the result of one member. But in other members, this friction is not necessarily increase the circulation. Friction does not necessarily increase the circulation. So, for example, this member, friction terms is negative. And in some cases, like this, baroclinic term is also large. So tornado strength may not depend on the origin of circulation. So it is difficult to estimate the tornadogenesis by the origin of the circulation. So then, to clarify what variable decides the tornado strength, we performed another analysis. This is the correlation of tornado strength to the several variables. This is the correlation between tornado strength defined by the 30 meter height maximum vertical vorticity and the mesocyclone scale maximum vertical vorticity. So and the horizontal axis is the time from tornadogenesis, and vertical axis is the height. So from this figure, the correlation between 1 kilometer height mesocyclone and tornado strength is very large. And this is the correlation between tornado strength and water vapor. This water vapor correlation is large, especially near the surface. And correlation to potential temperature is generally small. And this is a scatter diagram of mesocyclone scale vorticity here and water vapor here. So, and blue and green marks mean the member that generates the tornadoes. So you can see the member with large vertical mesocyclone scale vorticity and more water vapor is more tornadic. So high correlation. So these two factors is important to tornadogenesis. So why these variables are important is explained in this slide. So if a mesocyclone is strong, 1 kilometer height mesocyclone is strong, the center of mesocyclone, the pressure of center of mesocyclone is decreased. So below the mesocyclone, vertical perturbation pressure gradient force is generated. This is the upward acceleration, and it intensifies the tornadoes. And near surface water vapor is associated with the equivalent potential temperature near surface. So this is large. When this is large, equivalent potential temperature is also large. And level of free convection becomes lower, and buoyancy is stronger. And this is also upward acceleration. So these two force is important for tornadogenesis. And mesocyclone strength is largely correlated to the water vapor here and convergence here. Okay, so these variables are important to forecast the mesocyclone, not only mesocyclone but also tornadoes. This is a summary. So, okay, this is not about the data assimilation, but from this analysis, tornado forecasting tornado is associated to mesocyclone strength is important to the tornadogenesis forecast. So the mesocyclone strength of the mesocyclone is largely correlated to the water vapor and stronger convergence. So these variables should be corrected to assimilation. So using correlation to these variables to observations should be used. For example, ensemble-based data assimilation. Thank you very much.